Hello students, we are going to start chapter number 2 in 12th standard physics. I've already written it on our board. You can see the chapter name is mechanical properties of fluids. Okay, in this chapter we are mostly going to talk about fluids, its properties, fluids at rest, fluids in motion. Okay, this chapter has some basics in 11th standard, a chapter named mechanical properties of solids. Okay, it is bit related to that. So before you start this chapter, I would request you to go through mechanical properties of solids once. Okay, so let's understand what are fluids. Okay, I've already written any substance that can flow is fluid. Okay. Now, substance that can flow, liquid, agreed, gases will also come under fluids. Okay. So I've written the next line. Fluid is a phase of matter which will include liquids, gases, as well as plasma. Now, what is plasma? Plasma is the fourth state of matter: solid, liquid, gas, plasma. Okay, so plasma is also included under fluid. Okay, let's take example of lava. Okay, lava, it flows quite hot. Okay, so that is also termed as a fluid. Now, what does plasma contain? Okay, we just have to study this in very less detail. Okay, it will contain ions, it will contain free electrons, and it will contain neutral atoms. We don't have to go into much detail of plasma, just a brief idea. Now, here is one symbol that I have drawn, which is of shear modulus. This is the symbol for shear modulus, and it will be equal to 0 for fluids. So, shear modulus means the modulus that arises due to tangential force. Okay, there are two types of force we can apply. One is perpendicular force, and second is tangential force. Okay, so in case of fluid, the tangential force resistance by the fluid will be equal to 0. So hence the shearing modulus for fluid is also considered as 0. Okay. Now, in order to study this chapter, we have to assume few points regarding properties of fluids. I'm going to list some assumptions. Okay. These assumptions, let me tell you, are not sure that fluids will obey it. Like, let's take an example. If I tell you the first assumption that we are supposed to consider the fluids are incompressible. Okay. First assumption will be fluids are incompressible. Now, all fluids are not incompressible. They can be compressed to some extent. When we consider gases inside fluids, then gases are easily compressible. Okay, so this is one of the assumptions that we are going to study in order to study the properties of fluid. Second assumption will be the flow is to be considered as irrotational. Flow is to be considered as irrotational. Okay, flow is to be considered as smooth. No turbulence should be involved in that. Now, what do I mean by turbulence? Let's take an example of tsunami waves. Those waves are very huge. They might come in a form of a circle. So such flow is called as turbulence. In case of gases, think about hurricane, think about tornadoes. Those movement of air is in a form of a circle, turbulence. So we have to consider one more assumption, which is no turbulence. Clear? Then one more property we are going to consider, which is fluids will not have viscosity. Okay, so fluids will not have viscosity. You must have studied about viscosity. Like we have friction in case of solid on any surface. Friction exists in case of solid. Similarly, viscosity exists in case of liquids. So while studying this chapter, we are also going to assume that viscosity is to be neglected. Last assumption is the velocity of the flow is to be considered as constant. Velocity of the flow is to be considered as constant. Means whenever a fluid is flowing over a surface, you know that initially the speed will be faster, but after some time the speed will go on decreasing. We have to assume that velocity of flow will not decrease and it will remain constant throughout. So these are the four assumptions. Okay. Then we are going to study two more parts. In short, what are ideal fluids and what are real fluids. Let me tell you, for students also we have the same thing. We have some ideal students and most of the students are real students. Ideal students are those which obey everything, do their homework on time, follow teachers, okay? And real students, you can understand, you know very well, okay? So ideal fluids in this case are those fluids which have all these properties. Okay. One more thing I can add in ideal fluid is ideal fluids are subjected to normal stresses. Now, what do I mean by normal stresses? Okay, you have studied this stress in your previous standard that when we stretch an object, okay, it is under tensile stress. When we compress an object, then it is under compressive stress. Correct? So these two stresses, tensile and compressive, they are coming under normal stress. Now you will say, what about real fluids? In real fluids, apart from normal stress, shearing stress will also come into picture. As I told you, shearing stress, we are considering zero. That is for ideal fluid. But for real fluid, they have viscosity and hence shear stress cannot be considered as zero. So let me note this down. What I said for ideal fluid, normal stresses which will include compressive as well as tensile. Whereas in case of real fluid, viscosity is present, viscosity is present and shear stress cannot be taken as zero. Okay, so this is a brief introduction about this chapter. You can please take a screenshot of this. Okay, hello students. We are going to the next part of this chapter, which is what is hydrostatics. As I told you that in this chapter we are going to study about fluids at rest as well as fluids in motion. Like we had studied in our previous standard, objects at rest and objects in motion. So hydrostatics definition, I've already written it on the board, a branch of physics which deals with properties of fluids at rest is called hydrostatics. Similarly, we will have a topic called as hydrodynamics when fluids are in motion. Okay, colloquially. Okay, this is a term like having a meaning in normal use. So in physics, you have studied that fluids consist of liquid, gases, and plasma. But when you go to a doctor and doctor suggests you in case of hydration, drink plenty of fluids. So over there, in normal use, doctor is saying that drink plenty of liquids. Please don't use gases over there, okay? Because fluid is a term in normal use related to liquids. But in physics, we understand that gases are also included. Okay. Now we are going to proceed for one basic physical quantity, which is nothing but pressure. Okay, pressure, simple formula you have studied, which is force divided by area. Okay. Now let me tell you about this force. This force is nothing but the normal force, perpendicular force, which is exerted by the fluid on the walls of the container. Okay, that is that force. Okay, so here let's say we have to find out the units of pressure. Then from the formula you can easily make out that units will be, first unit is Newton per meter square. Second unit which you can write is Pascal. Okay, it is behind the name of a scientist, Pascal. Clear? And we are going to study one topic called as Pascal's law in this chapter itself. We have one more unit which is nothing but bar. Chemistry, you must have heard one bar. We have one more unit which is torr. It is also behind the name of a Italian scientist, Torricelli. Okay, let me write it. This is the spelling of that scientist. Italian scientist. Nowadays, Italy is quite famous in the world. And again, this scientist is from Italy. Okay. So these are various units. We have to understand that pressure formula, how it is used in daily life. I'll give you a simple example. Let's say I have applied a pressure of only 10 Newton on an object. Let me tell you, if I want to lift a coin of just 1 Newton, force is required to do that. Okay. So let's say force applied is 10 Newton on an object. Okay. The area of that object, let's say it is considered as 1 centimeter square. Okay. So we know the formula for pressure. Pressure is equal to force upon area, which will be written as 10 divided by 1. But this is in centimeter square. So I need to convert it into meter square. This will become 10 raised to minus 4. So this will become 10 into 10 raised to plus 4. And this will give you 10 raised to 5 Pascal. So did you understand what has happened? Just 10 Newton of force on a very small area causes a pressure of about 1 lakh Pascal. That's a huge value. So from this what we understand one thing, that if area is very less, then pressure can be a lot. Hence, objects like knife, okay, you can observe that knife has a very sharp edge, very sharp edge. Its area is very less. Okay, so when you cut an apple with that knife, okay, because of small area, too much pressure is generated and the apple gets cut into two pieces. Whereas the same thing you cannot do with the spoon, because spoon area is thicker. Am I correct? So this way you will understand the concept of pressure in detail. Okay, please take a screenshot of this. Okay, so students, we are going to proceed for a small derivation regarding another formula of pressure, which is going to be pressure is equal to density into height into acceleration due to gravity. I repeat, pressure is equal to density into height of the liquid column and acceleration due to gravity. This will be our last answer. Okay, so let us consider a container or a vessel filled with liquid having density rho. It could be water, it could be mercury, whatever. Okay, and we are supposed to find pressure at this bottom point A. Okay, so let's start this. We know basic formula of pressure, which is force upon area. Okay, in 11th standard we have already studied that force can also be written as m into g, mass into acceleration due to gravity. So therefore, pressure can be written as mg divided by A. Now we know very basic formula that density is equal to mass upon volume. I'll write density is equal to mass upon volume. So therefore mass can be written as density into volume. Substitute this again in this formula. So therefore we get pressure is equal to density into volume into G divided by area. Okay, now let's talk about volume. We know the formula for volume. We can write length into breadth into height for, let's say, a cube. Okay, length into breadth into height. Clear? Area formula, you know, it will be length into breadth. So instead of this part, length into breadth, I can always substitute area. So that is what I'm going to do. Instead of length into breadth, I can write area. So what you get finally, we finally understand that volume can also be written as area into height. So substitute this value over here. So therefore pressure can be written as density area into height into G divided by area. So now you can observe that these things can get cancelled. So finally we come to pressure is equal to density into H into G. I hope this matches. Okay, so this was a short derivation. On this derivation, we have some basic numericals, okay, which we will be solving in our next lecture. Okay, thank you. That's it for today.